We'll start looking at the microcontroller. And so embedded systems are used typically to interact with the outside world, either through some human-machine interface or with sensors, and then used to provide some response via actuators. And so in order to do this, they need to have input and output. So a microcontroller is a computer on a single chip. That means it has inputs and outputs, it has memory, and it has a processor. So the microcontroller that we're going to use is from the Atmel Corporation. We're going to use AVR microcontrollers. And so there are a lot of different microcontrollers. Here is a list of some 8-bit microcontrollers, which is what we'll work with, and then 32-bit microcontrollers. So there are different reasons to use these various ones. We're going to use the AVR microcontroller mainly because of the C compiler. It's as close to a standard C compiler as possible, and it's free. Another one, a popular one, is PIC. 8051 is the sort of the old standard in microcontrollers, and lots of courses are built around the 8051. So AVR microcontrollers have this naming system, and here's a little slide just talking about it. So first of all, they have the AT for the company that makes them, and then the group. So you can have a tiny, an AT tiny, or an AT mega, or then this classic group is AT90S, for example. And then the number after the group name, part of that number tells you how much memory it has. And so the way you determine the memory is the biggest number that's a power of 2. So here 128 is a power of 2, so this has 128K of memory. 4 is the biggest number that's a power of 2, so this has 4K of memory. All right, the I/O ports in the AVR are how the microcontroller interfaces with the outside world, so the input and output ports. Here is a pin diagram of the ATmega32, which is one of their microcontrollers. This has 40 pins. That's more than the microcontroller we'll be working with has. Ours has 24 pins. But they all share some of the same vital pins. So first of all, we have VCC and ground. So this powers the microcontroller. Whenever power is given to the microcontroller, then it starts to run its program. And so you connect this pin here to +5 volts and this pin to ground. These two pins are for connecting an external crystal. There's a built-in oscillator for the microcontroller that dictates the processor speed. So for the one that we're going to use, the built-in processor is 8 megahertz. If you want a different speed or a more accurate timer, then you can connect an external oscillator or a crystal using these two pins. Then we have a reset pin. Whenever this pin is brought low, it's like rebooting the microcontroller. It just starts over. It powers down and starts over its function. And then finally, the main topic of this video, the I/O pins. So these pins are grouped into, they're grouped into groups of 8 pins. So you can see port A, pin 0 through pin 7. So all of these pins, 33 through 40, these are the port A input-output pins. So we have A0, A1, A2, A3, 4, 5, 6, 7. And then there are port B pins, so they're over here, and port D and port C. So not all microcontrollers have all these ports. You know, if there are only 24 pins, and we can't have 32 I/O pins. And some of the ports might not have 8 pins. So we're going to look at one of these groups of pins because they're in groups of 8, and that's significant because this is an 8-bit microcontroller. So each one of these, for each port, there's going to be a register or a variable. And we'll get into that in a second. So finally, we have pins for powering the internal analog to digital converter. Analog to digital conversion is so common and microcontrollers that they have built-in circuitry for it, and it takes separate power for that circuit. Okay, back to the ports. So here is a slide showing the concept that for each set of 8 pins, so each I/O port, there are 3 variables or registers associated with it. So we call these registers the data direction register, DDRB, the port register, so port B, and the PIN register. Here's pin B. And then you have the same thing for port A. So you got DDRA, port A, and pin A. And it's referred to like this. So for a given port, so port X, you have pins X0 through X7. And for each of those 7 pins, there are 3 registers associated with it. And so you can see that this register, or this variable, is an 8-bit number. And each bit of the register corresponds to one of the pins. So the DDRX register, so DDRX pin 6, or bit 6, excuse me, corresponds to pin 6 of that port. Each of these 3 registers has a certain function, and we'll talk about that later. First of all, the DDR data direction register. This variable or register determines whether or not a pin is used as an input or an output. So if it's an input, then that means the microcontroller is using that pin to check the voltage, or check the voltage is checking the voltage at that pin. So for example, if we have a switch that connects a pin to ground or not, then that pin would be an input. So data is going into the microcontroller. Or an output would be used to control some kind of actuator or a light. So an output would be sending data out, so we could connect an output pin to an LED, and then we could write a program to turn that LED on or off. So that's called an output pin. And all these pins can be used either for input or output, and the way we set it up to make it input or output is with the data direction register. So you see here that data direction register, if it's 0, then that means it's an input pin. If DDRX is a 1, then that pin is an output pin. So if we wanted to make port B pin 0 an output pin, then we would make bit 0 of DDRB a 1. Because if that was a 1, then that pin would be configured for an output. And then the port X register has 2 functions. If the pin is an input, port X either enables or disables the pull-up resistor, which we'll talk about at the end of this video. And if that pin is an output, then the port X register either sets the voltage to be high or low on that pin. For example, if we had port B pin 0 as an output, and we wanted to go to 5 volts, then we would write a 1 to the port B bit 0, to the port B register bit 0. So if this was a 1 and this was a 1, then this would be at 5 volts. And if we instead wrote a 0 to the port B register bit 0, then this would be at 0 volts. I know that's a lot to take in right now, but we'll look at some more examples in a little bit. So we're going to program these microcontrollers in C, and this will be in the next video.